my presentation is called Pompey's Pillar National Monument Rock Stabilization. I'm going to talk about the preliminary results, and I'm also going to talk about the ongoing work that we're doing right now. And I worked on this project with Lee Peterson and Ryan Peterson. So this project is located right adjacent to the Yellowstone River, about 30 miles east of Billings, Montana. And it's managed by the Bureau of Land Management. So Pompey's Pillar is approximately a 200-foot tall sandstone outcrop. So on this map here, it's right here. Obviously, the Yellowstone River runs right through there. I want to talk a little bit about the history at Pompey's Pillar. So Pompey's Pillar has been an observation point for more than 11,000 years of human occupation. It exhibits hundreds of markings, petroglyphs, and inscriptions left by visitors, including American Indians, Captain William Clark, Sacagawea, and her 18-month-old son, which is why it's called Pompey's Pillar, and as well as European fur trappers, Yellowstone River steamboatmen, etc. So there's a lot of people who inscribed on this rock. So when you visit the site, it's pretty cool. You can see all the signatures. And I also wanted to include a close-up of the William Clark signature. So Itasca was contacted by the Bureau of Land Management. They had 3 areas of concern. Primarily is the signature block area, which is located here. The William Clark signature is, actually I need to get a pointer out so you guys can see where I'm pointing. Okay, so signature block area is located here. The William Clark signature is approximately right here. There's a boardwalk that runs along the site, so visitors can walk up here and view the William Clark signature. Additionally, we were asked to look at Turtle Rock. Turtle Rock is called Turtle Rock because there are 2 separate rock blocks that form what looks like a turtle. So this is the turtle head right here and the turtle body right here. And the back joint is this large open joint that separates the turtle body and turtle head from the adjacent rock. And thirdly is this lower rock area. There's a bunch of sandstone blocks that appear to be undercut, and those are located right adjacent to the visitor boardwalk. It's not letting me move forward here. Hold on. Okay. So in the signature block area, this is what it looks like. This was one of the images we got from the site visit. There are large open joints that create the signature block. The sandstone is then underlain by approximately 10 feet of this weathered shale and siltstone that I'm highlighting here. So the undercut sandstone in combination with these large open joints obviously creates a risk for block toppling. And prior to the site visit, we already separated the blocks into 3 different blocks. Block 1 is separated by these 2 large open joints. Block 2 is separated by this large open joint and a joint on the northeast face right here that separates block 2 and block 3. And again, just for reference, the Clark signature is located approximately right here. So this is what the Turtle Rock area looks like. This is the Turtle Rock head and the Turtle Rock body. And there's that large open joint that separates the Turtle Rock body from the adjacent rock. So the shale and siltstone layers at Turtle Rock have weathered and eroded, undercutting the upper sandstone and creating all these overhangs that you see in this image. And there are also obviously many large open joints that you can see. So in this area, there's also a risk for block toppling. And finally, this is what the lower rock area looks like. Sandstone blocks are located adjacent to this boardwalk, and many of which are undercut by that eroding shale that you can see in this image. And we also found that there are many open back joints for some of the blocks in this area, which increase the risk of block toppling for the lower rock area as well. I wanted to talk a little bit about the geologic setting. The main area in the signature block is what we're calling this upper sandstone, and that weathering, eroding shale siltstone layer is located right here. And you can see in this image, it's undercutting the upper sandstone. Pompey's Pillar is part of the Lance Formation. It consists of alternating beds of sandstones and shales. It's approximately 700 to 1,500 feet thick and is underlain by the Bear Paw Shale. The geometry at Pompey's Pillar is largely formed by the adjacent Yellowstone River. So to kick off the project, we wanted to do a site investigation. The site investigation was conducted over 4 days in July of 2020. The purpose was really to collect as much geometry as we could at the site. The geometry of the rock blocks, of the joints, is hugely important. So we wanted to get as much data as we could. And we also wanted to install initial monitoring equipment at several locations. So to perform these tasks, we had some help from Bolton and Menck, who provided the geometry capture services, including LiDAR scanning, photogrammetry, and surveying. And we also had help from BAR, who installed all of the initial instrumentation. So first, Bolton and Menck conducted a drone survey to capture the high resolution photos and videos of the entire outcrop. So this is the orthoimagery that was generated by Bolton and Menck. They georeferenced using a network of aerial ground control, and then they used Pix4D software to process the photos and then generate the point clouds. And that'll be very important when we create our 3-deck models eventually. And Bolton and Menck also produced the orthoimagery and the textured meshes. And the table on the right here, you can see all of the images and data that was collected by Bolton and Menck and sent to Itasca. So BAR installed instrumentation during the July 2020 site visit. They installed 5 remote reading rock monitoring instruments. First was a distance meter mounted on a rock near the rail fence down here and pointing at block 1. So this is block 1 here. And then there's also a distance meter mounted under block 2 here, and 1 crack meter on the north face of block 2 and 1 crack meter on the east face of block 2. And finally, in the Turtle Rock area, we wanted to install a crack meter across the joint that separates the body of the Turtle Rock from the adjacent rock mass right here. And this is what the installed crack gauges look like on block 2. There's one right here and one right here. So the data from the site was imported to a web-based data visualization program called eagle.io. And BAR managed the telemetry, data acquisition, and web-based data presentation with direction from Itasca. And then Itasca staff monitored the data, and then we would notify any stakeholders or a BLM of any increase in movement or anomalies that we're seeing on the site. So the point clouds, meshes, and photographs captured during the site visit were used to identify and extract the location of 72 joints. The joints ranged in size from a few feet to tens of feet. These images are showing what it looks like in cloud compare. That's what we use to segment the joints. And then we fit a best fit plane to each of the joints to get the actual geometry. And obviously this procedure is best when you have these flat planes, such as this here, that are trending in the same direction as the rock surface. But if the joint trends perpendicular to the rock surface, like these joints in here or in here, this process can be a little difficult to capture that geometry. So this is what it looks like with the joints with all the mesh on. And this is what it looks like with the joints isolated and the planes. So we isolate those planes and then capture the geometry of those and add those into our 3-deck model. And of course, we plotted up a stereo net. We found 5 joint sets. And this image shows just the clustering of the joint sets that we found. The next thing we wanted to take a look at is how the joints intersected the rock outcrop. So all of these green lines here, those are all the joints that we found. And one thing we wanted to point out that we noticed is that some of the joint sets that in this slide, so joint set 5 is roughly parallel to the northwest face of the rock, and set 3 is roughly parallel to the southwest face of the rock. So we found that to be interesting. So next, we wanted to take all the site information we collected and then look at the rock block stability. So we used the photographs, the point clouds, and we identified all the joints and bedding planes, like I had explained in a few earlier slides. Then we extracted the location, orientation, and extent of the joints. And then we used the 3D mesh to get like the actual geometry of the 3 different locations, the signature block, turtle rock, and lower rock. And then we imported the mesh, all of the geometry information, the joints and the bedding planes into a CAD software that we use at Itasca called Rhino. And then from there, we wanted to intersect everything and create these individual blocks. So we used our software called Griddle that does that. And then Griddle also will discretize the zones inside the rocks, or inside the rock blocks, and generate the volumetric grid. And so once we have our final volumetric grid, we can then import it into 3-deck. And that's what we use to develop our rigid block model. And from there, we conducted our stability simulations. One of the big uncertainties for the stability simulations is the support provided by the shale and siltstone. So I like this image because you can really tell in some locations how undercut the sandstone is. The accessible shale and siltstone layers near the signature block was sounded during the site visit. The layer was drummy in some locations. 80 to 90% of the rock surfaces sounded during the site visit showed signs of being hollow and loose. So the area, the area near Turtle Rock was inaccessible, but we assumed it was the same. And this led us to believe that the shale and siltstone layers do not provide significant support to the overlying sandstone block. And in order to account for this in the model, we decided an incremental amount of shale and siltstone should be removed from the model, and block stability should be assessed at each stage. And I'll explain more about that in a few slides. We use 3-deck to conduct the stability assessment. 3-deck is a 3-dimensional numerical modeling code for advanced geotechnical analysis of soil, rock, groundwater, etc. 3-deck is the appropriate software for this project because this rock is heavily jointed, heavily bedded, and we really want to capture that behavior. And the numerical formulation is based on the distinct element method. Again, this is just showing the 3 blocks, block 1, block 2, and block 3 in the signature block area, and because I'll be referring to these blocks in later slides. So this is what all of the joints look like imported into Rhino with the mesh. So you can see the mesh and the joints that have been extended to cut through the model. And then once everything's been cut in Rhino, we import it into 3-deck. And this is what the joints looked like. The final version of the joints looked like in 3-deck. All of the gray you see here, that's all the bedding planes. And then the brightly colored planes are the joints. And then this is what the final rock blocks looked like in 3-deck. And again, to examine the stability of the undercut sandstone, the maximum extent of the weathered shale was traced around the signature block. So this yellow line is that trace of the maximum extent of the shale, which we're calling the shale limit. And you can see from this image how undercut that shale is in some place, or that sandstone is in some places. So incremental amounts of shale were removed from the model. So we started with the original geometry, which would look like this. And then we removed 1 foot of shale and siltstone, 1.5 feet, 2 feet, and then finally 2.5 feet of shale and siltstone was removed from the model. And that's just to simulate what it would look, how the model would react with the loss of the underside support. Here are the 3-deck modeling results. All of these plots are showing displacement contours where red is more movement and blue is less movement. And the lines that you're seeing on the chart, those are displacement histories. So in order to track the stability of the individual blocks, we tracked the movement of the individual block with these displacement histories. And if the displacement remains constant or flat, like here, we assumed that that block was stable. And based on all these histories, all of the blocks appear stable in this rigid block analysis. So here we have 5 plots for 5 different shale increments, 0 feet of shale movement, 1 feet, 1.5 feet, 2 feet, 2.5 feet of shale removal from the model. And this prediction aligns with observations during the site visit, as all of the greatest predicted movement happened to be on block 1, which then we divided into 3 subblocks, which you'll see on the next slide. So this is block 1, where you're seeing all the movement in the previous slide. So we divided into block 1A, block 1B, this red block is block 1C, and then adjacent is block 1D. So block 1A was defined by an open joint along the backside here. And underneath, there's a small rock ledge that appears to be supporting the base of that block. So the open back joint along with that small block ledge means that it is a potentially hazardous block just based on its geometry. And block 1B is cut by joints on all sides and is also heavily undercut. You can see there was likely a sandstone block underneath here that had fallen out at some point. And block 1C is defined by these 2 large open joints here on the northwest and southwest sides. Next, I'm going to look at the Turtle Rock area 3-deck models. So we divided Turtle Rock area into 5 blocks. Block 1 was divided into 3 blocks, 1A, 1B, and 1C. And block 2 was divided into 3 blocks as well. And again, this is what the mesh and all of the joints that cut the model look like in our the CAD program Rhino. And then we cut the model, imported into 3-deck, and then this is what the final jointing looks like when it's imported into 3-deck. And then finally, what the rock blocks look like in 3-deck. Again, this is what the maximum shale extent in the Turtle Rock area looks like. It's this yellow line here. And in order to assess the stability, we use an incremental amount of shale removed from the model. So first we modeled the original geometry and then removed up to 2.5 feet with half-foot increments in the Turtle Rock area. Here are the 3-deck modeling results. Again, this is all displacement contours, with red being more displacement and blue being less displacement, and with all the histories along the rock blocks. So the figures show that block 3, which is this block, the tall, thin block that's right next to the Turtle Rock body, that's not stable for the current shale siltstone configuration. And you can tell that based off of this history right here. It's really not leveling out. The The simulations for the additional shale and siltstone erosion show that the block movements obviously accelerate for that block. And after 2.5 feet of shale siltstone removal, the block immediately adjacent to it, block 4, which is this block, also becomes unstable. But the turtle rock head and body blocks show some movement with increasing erosion, but appear to be stable in this analysis. So the predicted instability based on the 3-deck models, that was compatible with what we were seeing at the site. This red dashed line is the joint separating the turtle rock body from the rest of the pillar. And then this red highlighted area is the face of block 3, and this was the block that was predicted to be unstable. These yellow dashed lines are the surface expression of the 2 joints parallel to this red highlighted joint. So we believe that the red joint surface was originally in line with this trace at some point, but it's now offset about 2 feet. And the 2 yellow joints back here are open by about that same amount, by about 2 feet. So the block has moved and appears to be marginally stable. So this is what the lower rock area looks like again. The rock blocks are actually from the lower sandstone, so it's below that eroding shale siltstone. Because of the nature of the geometry of the blocks in the lower rock area, we did not conduct a rigid block analysis like we did for the signature block and the turtle rock areas. So the lower rock area instability seems to be related to the behavior of individual blocks, since those blocks are undercut due to underlying shales. And this lower image kind of shows how eroded it is underneath some of those sandstone blocks. We identified 3 lower rock area blocks in particular that appear to be the least stable. And this is based on open back joints that you can kind of see in this image. And they also exist outboard of adjacent rocks. But the entire lower rock area shows signs of ongoing rock movement, weathering, and breakage. So this is just another image showing how heavily broken that area is. Phase 1 findings and recommendations. So at the signature block, the various subblocks of block 1 were found to be the least stable. So in late July 2020, Itasca recommended moving and extending the visitor barrier at the pillar due to observed condition and the measured movement of block 1. And Itasca recommends that the boardwalk remain closed until some phase 2 tasks are complete due to the risk associated with signature block 2. And at Turtle Rock, blocks 3 and 4 were found to be the least stable. And we also identified 3 lower rock area blocks that were the least stable based on observations. So now I'm going to talk about what we're doing right now in phase 2 and give you a little status update. So to kick off phase 2, we wanted to do another site visit because we really wanted to refine our geometry. We wanted to get more information about the rock mass and rock characteristics. We went back to the site over 3 days in the beginning of March 2021, and representatives from BAR came to the site in mid-March to install updated monitoring instrumentation. First, we wanted to look at the sandstone layer. We obviously rented a crane so that we could get up close and personal with the sandstone this time. We wanted to measure roughness, aperture, infilling, orientation, and in particular, connectivity with other joints that are creating these blocks. We really wanted to get the geometry correct. And for the siltstone layer, we wanted to do more sounding of the shale and siltstone. We wanted to measure some of the undercuts in the lower rock area as well as the signature block area, and kind of measure how much the shale and siltstone has sagged away from the sandstone. We also installed telltales in the siltstone. That way we can track the rate of erosion, and it's also a tool for the BLM to use in the future in case they want to track erosion of that siltstone. And on site, we used a Schmidt hammer to get an understanding of the comparative strength of different areas of the siltstone and sandstone. And this was then compared with lab testing data to determine the relative strengths. So we collected 5 core samples to be sent to the lab for UCS and Brazilian testing. We drilled into a previously fallen sandstone block for 2 reasons. One, access to the pillar was difficult, and we also didn't really want to alter the actual pillar. And we also collected some grab samples of the siltstone layer to get a better understanding of the composition of that layer. We updated the instrumentation in all 3 areas. In these images, all of the green arrows and green notches, those are existing, and all of the blue arrows and blue notches, those are the new instrumentation. So now on site, there are 3 crack meters along the top of block 1, seen in this image. There are 3 crack meters along the faces of block 2, and 3 distometers on the faces of block 1 and 2. And in the Turtle Rock area, there are now 4 crack meters installed at these locations and 1 tilt meter. In the Lower Rock area, we installed 3 tilt meters at the locations where we identified the blocks with those open back joints. In this phase, we're also doing a rockfall analysis, and the software we're using is Traject 3D. So we're using different block sizes and shapes, and the block sizes are based off of what was measured, the blocks that had previously fallen along the slope. And we drop from different locations along the edge, and we use this information to inform the burial location and stay out zones. So this is what the latest and greatest 3-deck model looks like. It's obviously much more detailed than the previous model. We are updating the rock mass properties based on the lab test data that we got. And we're converting the models to a deformable model instead of using the rigid block model that we used in phase 1. And we're also really making sure that we get the locations and the orientations of all the joints in the bedding planes as accurate as possible. And this is the continued work for this project. So we are running simulations with incremental shale and siltstone removal. We're also planning on removing entire large blocks. So in the signature block area, we're going to be removing the entirety of block 1 to see how the stresses in the adjacent blocks react to that. And then in the Turtle Rock area, we'll be removing blocks 3 and blocks 4. We're also developing a TARP plan, continually monitoring the instrumentation data, and eventually developing the stabilization plan, which we will also be modeling in 3-deck. So that's all I have for you. Thank you for your attention.
All right.